Hi everyone, Mike here, and I'm confident you'll understand confidence intervals when we're done. Sort of, possibly, hopefully. We're talking about confidence intervals right now. And the setup is, as usual, there's a population of interest. It's got a mean, it's got a population mean, it's got a population proportion. It could be high school students in the United States, and what's the average GPA of senior high school students in the United States. It could be what percentage of high school seniors in the United States prefer Rocky Road ice cream to all others. So there's a true but unknown mean of interest. There's a true but unknown proportion of interest. Now, how do we form guesses? We take a random sample of n items and we form our guesses. X bar is a guess of mu. The sample proportion is a guess of p. How wrong are we? How good is our guess? It'd be grossly misleading to say that our guess equals the true value. We're probably off by a little bit. And how off are we? Well, you can form what are called confidence intervals, and another name for that would be called interval estimates. Here's an example of what they look like. What's the average weight of graduate students at Harvard? 0 is the, let's see, it looks like this is the men. I forget how this is coded. These are the women. And this is what an interval estimate looks like. We're pretty confident that the true average weight of men is between 163 and 173. We're pretty confident the true average weight of women is between 119 and 133. We call those interval estimates. The sample means are called point estimates. They're estimates of single values. The interval estimates give you lower and upper bounds. That stands for lower limit and upper limit. You can do the same thing for proportions. What proportion of students are right-handed? Between 86 and 97% of men are right-handed. Between 91 and 1.01. That's silly because the upper bound should be 1. I don't know why it gives you a value bigger than 1. Are right-handed. So again, an interval estimate gives you a lower and upper bound, and it's a sense of how good your guess is. The wider the interval, the worse your guess. The narrower the interval, the better your guess. And that's what an interval estimate is. A point estimate's an estimate of a single value. What we want to do right now is figure out how to get a lower and upper bound for this interval estimate, also called a confidence interval. The general estimation process is there's a population of interest, there's a mean mu, which is unknown. You take a random sample, you get X bar, and then you're able to make some statement. I'm pretty confident that true unknown mu is between 40 and 60, say. How does it work? It's just about 2 or 3 slides of theory, and then we can do it. The central limit theorem says X bar is normally distributed with mean mu, variance sigma squared over n. That's how we used to write it. We write it now like mu sigma over root n. Sometimes people put the variance here or they put the standard deviation. This is the old style with the variance. Let's do the standard deviation. So central limit theorem says if n is large, X bar is normally distributed around the true mean mu with standard deviation given by sigma over root n. We then z-score. Subtract off the mean, divide by the standard deviation. When you z-score, you get a normal 0, 1. So that's idea 1. Now, this is the same idea from the previous slide. Your normal 0, 1, because your normal 0, 1, 95% of the area is between minus 1.96 and 1.96. So this thing is a normal 0, 1, and we know the probability is between minus 1.96 and 1.96 is 95%. Let's stare at this thing for a minute. This is a probability statement. It's a probability statement about what? What is random? X bar is the random variable. X bar depends on the sample we get. X bar is random. Mu is a fixed quantity. Sigma is a fixed quantity. N is a fixed quantity. X bar is the random quantity. This is a probability statement about X bar. So we have the probability X bar minus mu, that junk is between minus 1.96 and 1.96 is 95%. We do a little algebra, and we're able to isolate mu in the middle. But this is still a probability statement about X bar. We then drag out the lower and upper bounds, and we make the following statement. We call this, and we went from big X bar to little X bar. This is the random variable. This is data. Once we collect data, we have a little X bar, and we make this statement. This is called a 95% confidence interval for the mean mu. We're 95% confident that the true mean mu is somewhere in this interval. Now, this is a really weird expression that we only use for confidence intervals, this idea of confident. What does it mean? We're confident in the process. We're not confident that any one interval actually contains the true value mu. We're confident in the process. And what we mean by that is if we build 100 such intervals 95 out of 100 should contain the true value mu. Any one interval, we're not really sure, but why do we use this? We're confident in the process. Jerzy Neyman, a really famous statistician on the West Coast, the parameter is an unknown constant, that's mu, and no probability statement concerning its value may be made. You can't say anything about the probability mu is in some interval. Confidence intervals are weird things. We're confident in the process of how we make them, and so we use them because most of the time, they are correct. To say we are 95% confident is shorthand for 95% of all possible samples of a given size from its population will result in an interval that captures the unknown parameter. The typical example of this is this, where we show you many intervals. Most of them do contain the true value. So the true value mu is that black line there. Most of them do contain the true value. Good, 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 good. Oh, this one too low. So we use confidence intervals because most of the time they work fine. 95% of the time they're good. 5% of the time we're going to make a mistake. As an example, here's a graph of many intervals. You can see missed, 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 missed. Most of them, though, do contain the true value, which is right in the middle here. Creating intervals, working with them, really straightforward. As part of the quality control program, Whole Foods wants to know the average weight of grapefruits they purchase from Florida growers. They take a sample of 40 grapefruits with mean this, that's X bar, and we know from past experience that the standard deviation is 1.75. It's now plug and chug. The 95% confidence interval for the true mean weight of Florida grapefruits is then this. The true mu is somewhere in this interval. If the contract says, on average, we're going to give you 12-ounce grapefruits, you'd say, yeah, looks like they're 12 ounces. If the contract says, on average, we're going to give you 13-ounce grapefruits, you'd be like, no, you're not doing that. You're not giving us 13-ounce grapefruits. If the contract said, on average, we're going to give you 11-ounce grapefruits, you'd be happy because they're much larger than 11. So the true mu is somewhere in there. We're pretty confident the true average weight of grapefruits is between 11.31 and 12.39. There's a problem, though. If you look at this formula, and this is a shorthand for writing the formula, there is an issue. It assumes you know sigma. And we always start out by saying, yeah, assume you know sigma, but in reality, you never know sigma. So what do? Well, you replace sigma by S. You have nothing else to do. What else would you plug in? So this is the interval you use, and this assumes n is large. We'll show you what to do for small n. But if n is large, bigger than 30, you replace sigma by S, and you get that confidence interval formula. So again, assumptions. This is how we derive the interval. It should be this. Central limit theorem gives us this interval. In general, we don't know sigma. Replace it by S, and you get that interval. As an example, is it hot in here or is it just you? That was one of my college roommates' pickup lines. Never worked well. What are we always told normal body temperature is? Well, we're told it's 98.6. Where'd that number come from? Some German researchers did it and discovered that the average body temperature is 36.83 Celsius. If you round that up to 37, which we would do because we're Americans, we always round numbers up, you get 37. You then convert 37 Celsius to Fahrenheit, you get 98.6. Aha, that's where 98.6 came from. So some University of Maryland researchers wanted to recreate the study and see if true average body temperature was 98.6. Here's their data. Really interesting looking. Goes far down and far up. These are, quote, healthy people, unquote. And the t-test command, if you give it a data set, will give you the confidence interval. So here we get the confidence interval. You can do it by hand if you want, but we get the confidence interval is 98.07, 98.31. You can convert it. That's in Fahrenheit. You can always convert to Celsius. What's interesting is what is not in that interval. 98.6 is not in that interval. So we're pretty confident true average body temperature is somewhere in the interval. That's the interval. It doesn't include 98.6. What's interesting, though, is what did the German researchers say? 36.83. 36.83 is a plausible value. It is in that interval. So we sort of reaffirmed the German study, and we also said, no, 98.6 isn't true average body temperature. In fact, it seems to be lower than 98.6. Again, if you're wondering what's going on, there's S and S of root n. You can form two intervals. There's x bar plus or minus 1.96 times S. There's x bar plus or minus 1.96 S over root n. S tells you how variable your sample is. This interval would sort of tell you where most of your data lies. S over n tells you how variable x bar is. This interval will tell you where mu is. So S refers to how variable your data is. S over root n refers to how variable x bar is. Some more examples. Now, sometimes you just have the summary statistics. Often on homework problems, you just have summary statistics. The BSDA package has a nice routine called tsum.test for summary statistic, and it's a nice package to use. As an example of using that, a random sample of 121 automobiles traveling on an interstate showed an average speed of 65 with a standard deviation of 22. Find the confidence interval. Great to use the tsum test there. You give it n, you give it the mean, you give it the s, then you get the confidence interval down here. We're pretty confident. Average driving is 61 to 68.95 miles per hour. You can find any size interval you want. This is the 95% confidence interval, but if you want a different size, what changes is what goes in the box there. There's some strange notation called z alpha over 2. It's such that the area to the right is alpha over 2. Here's a better looking picture. 1 minus alpha in the middle, minus the alpha over 2 has alpha over 2 to the left. Positive z alpha over 2 has alpha over 2 area to the right. 1.96 gives you 0.025 to the right. And here are some of the common ones. If you want a 95% interval, it's 1.96. An 80 would be 1.28. A 99 would be 2.58. These are some of the common confidence intervals that people use. And what happens as confidence goes up? What has to happen to the width of the interval? Well, 100% confidence interval is always going to be what? It's always minus infinity to infinity. It's really not useful, but this shows you that as your confidence goes up, the width of the interval is going to get larger and larger. That's what we're showing here. What's the fastest you ever driven a car? Well, here's data from a class survey. These people were really unclear on. This was the Richard Petty experience. Someone got a graduation present, the Richard Petty experience, and they got to drive a race car really fast. So here we see what's going on. Now, let's do a 80%, 90, 95, 99, 99. What happens as with the confidence gets higher and higher, the interval gets what? Wider and wider. Because you're more confident. I'm really confident I know where the true mu is. Well, there's no free lunch. To be more confident, the interval has to get wider and wider. So there's a trade-off. You want narrow intervals and high confidence, but you're not always going to get that. So we usually fix confidence at 95, hope for the best. If you want narrower intervals, usually you want to collect more data, because look in the bottom here. Ends in the bottom there. You get more data, you're going to get a narrower interval. But the general rule of thumb is that your confidence level goes up, the interval will get wider and wider. We call this thing the margin of error. There are three things that really affect the margin of error. How much noise is in the system, how variable your data is, that affects the margin of error. And the more data you have, the narrower the interval. And it's called the confidence level or the confidence coefficient. And that affects it. As you get higher confidence, it gets wider. Lower confidence, it gets narrower. Now, finally, what do you do about small n? So central limit theorem gives us this result. We said if n's bigger than 30, no foul, we're going to replace sigma by s, and we approximately get this result, and we can work with our confidence intervals. What if n is small? Well, in general, you get this result that x bar minus mu s over root n follows what's called a t-distribution. Not a normal 0, 1, but what's called a t-distribution with what we say is degrees of freedom equal to n minus 1. Well, what's the t-distribution? The t-distribution looks like a normal 0, 1, but has fatter tails. So formally, when sigma is not known, the sample size is less than 30, the data is approximately normal, it's not too skewed, then this thing is a t, follows a t-distribution. It was developed by William Gossett. He was a statistician for the Guinness Brewing Company. He was working with small sample sizes and realized his regular confidence intervals he was using weren't good. They were wrong more than 5% of the time. And he came up with the t-distribution. Well, using the t-distribution, your 1 minus alpha times 100% confidence interval works very much like what we did before, but you have not 1.96 here. It's supposed to be an arrow. You have what's called a t. Is a different value you have to look at that makes the interval wider. So the bottom line is you're replacing sigma by s. You don't have a lot of data. You're replacing sigma by s. You don't have a choice. There's nothing else to put in for sigma. But by doing so, you're introducing more variation, more uncertainty. How's that reflected in the interval? The interval should be slightly wider, and that's what you get. Instead of 1.96, you're going to use some kind of t value there. The t looks like a normal 0, 1, but has fatter tails. As the sample size gets larger and larger, the t looks more and more like a normal 0, 1. So showing an overlay here of different t's and a normal 0, 1. As sample size gets larger and larger, the t looks like a normal 0, 1. Here's a comparison, and you can see after a while, you can't even tell that there are two different curves here. So in general, how do you create a confidence interval? It's x bar plus minus some t value, which we find from a table or r, s over n. We're pumping up the volume. We're replacing sigma by s, introducing more uncertainty, so we have to make the interval wider to account for that. As an example, this is what a t-table looks like. The thing here is what you'd use in the middle for 95% confidence intervals. If you want to get these values in R, it's just a QT command, that's called a t-quantile, 0.975 in your degrees of freedom, and that would give you all these values here. To show you how to use this table, degrees of freedom is n minus 1. If you have n equals 2, if you have 2 data points, and you want to compute a 95% confidence interval, first of all, you're a doofus. Because you're trying to do something with 2 data points. That's crazy. It would be x bar plus minus 12.7. Why is it such a big number? Because you're being an idiot, and you're trying to create a confidence interval with 2 bits of data. If n equals 29, that makes a lot more sense. It becomes 2.048. And eventually, it would become 1.96. That actually happens around n equals 100 or so. But it gets smaller and smaller, and eventually it becomes 1.96. As an example, random sample of 15 students slept on average of 6.4 hours last night with a standard deviation of 1 hour. Find the confidence interval. We got to use the t, so it becomes 2.14 here, not 1.96. Small data set, 2.14. Your confidence interval is 6.4 plus 0.55. Behind the scenes, t.test, that gives you the confidence interval in R. It's called t.test because it's using the t all the time. tsum.test, also called t, is using the t all the time. We always replace sigma by s. So really, irregardless of sample size, we should be always using the t. A lot of people say if n's bigger than 30, I don't care, I'll just use 1.96. But again, we're always replacing sigma by s. So to be safe, we would always use the t, use t.test in R, or use the qt command to find the right t value when we create our confidence interval. One caution when you use the t, especially when you have small samples, is that if n's bigger than 30, central limit theorem kicks in. You don't really worry about skewness in your data. If n's less than 30, you might worry about that. Are you skewed? Do you have a lot of outliers? This procedure may not work if n is less than 30. However, it is pretty friggin' robust. Unless you have some insane, extreme outliers, this method is good to use, and that it means it can create confidence intervals for small data sets, confidence intervals for large data sets. It's a pretty robust method and really hard to actually mess it up and not work correctly. When does the t method not work? If you have binary data. So if you're doing proportions, if you have yes, no responses, it doesn't work. If you have extreme outliers, it's not going to work. Especially when n is small. If you have extreme outliers, don't try this. There are what are called non-parametric methods that are better to use. One final example just to show you that very straightforward to do this. Random sample of 35 men yields a mean pulse rate of 72.5 beats per minute, standard deviation of 10.2. Find a 95% confidence interval for the mean pulse rate of all men. We're going to give it the tsum.test command. We just give it n, the mean, the standard deviation. We're pretty confident the true mean pulse rate of all men is between 68.99 and 76.00 beats per minute. As assumptions, whenever we're using the t, what do we want to assume? Our data is independent. We took a random sample. Ideally, our sample size is a lot smaller than our population size. There are little fixes we have to do if that's not the case, but in general, we assume that's the case. If the sample size is small, it's not in this case, but if the sample size is small, we want to make sure the data is not highly skewed or has a lot of outliers. For large data sets, we don't care. Central limit theorem kicks in, so we don't really have to check the assumptions as much for large data sets. Hope that helps a little bit with confidence intervals And next up was going to be hypothesis testing. Hope you're having a great day.